Alrighty, why don't we go ahead and get started? Good afternoon and welcome to today's webinar titled Precision Lubrication Strategies for Metal Forming Operations. The webinar is presented by Spraying Systems Company, hosted by Metal Forming Magazine. My name is Brad Kubin. I'm the editorial director at Metal Forming here at the Precision Metal Forming Association, and I'm pleased to serve as your moderator today. So before we get started, just a few notes about today's session. It is being recorded for archiving, and the recorded event will be posted to our website, metalformingmagazine.com, within the next few days. We'll let you know via email when that recorded webinar is available for viewing online. Also, all of the participants in the meeting are in listen-only mode, which means that our speaker and any other listeners cannot hear any audio from your site during the program. But you can communicate with us throughout the program by submitting any questions and comments you have by using that question box, which is located on the right-hand control panel of your Zoom screen. If you don't see the Q&A panel, just click on the More button and it should appear. Then you'll simply type your question to an organizer as selected from the drop-down menu. Then you'll use that same question panel to ask questions of our speaker at the end of the webinar. So now it's time to begin the session. Effective lubrication is essential to ensure part quality, tooling performance, operational efficiency, and worker safety. So the presentation we're going to hear today shares best practices for improving lubricant application through precision spray technology. We'll discuss strategies to reduce over-application, to minimize lubricant waste, and improve coverage consistency, while at the same time decreasing overspray, misting, and cleanup. We'll also hear some insights regarding nozzle selection, spray placement, flow control, automation, and line speed-based application to help stampers apply the right amount of lubricant exactly where it's needed. So our presenter today is Sam Scully. Sam is a design engineer at Spraying Systems. He pre-recorded this presentation, and then he'll join us live after the presentation to take your questions and comments. So please give some thought to your own processes and press room lubrication related challenges, and be ready to pose your challenges to Sam at the end of the webinar during the Q&A session. So without further ado, let's go ahead and launch the webinar and welcome Sam Scully.
Good afternoon, everyone. Welcome. My name is Sam Scully. I'm a design engineer with Spraying Systems Company, and this is Precision Lubrication Strategies for Metal Forming Operations, presented with the Precision Metal Forming Association. We'll give people another minute or so to join. While we're waiting, today is about one idea. Lubricant application is a process variable, just like press speed or tonnage, and when you control it, the results show up directly in cost per part. We have about 35 minutes of material. At the end, we'll hold for the last 10 minutes for questions, so please drop them in the Q&A panel as we go. Let's get started. Just quickly, who I am and why I'm the one talking to you. I'm a design engineer at Spraying Systems Company. My job is designing and specifying spray lubrication systems for stamping, roll forming, and fabrication plants. Everything from a single lubrication point at one press to closed loop application across a full coil line. Spraying Systems has been doing this for over 90 years across more than 200 industries with more than 12 manufacturing plants globally. I'm not saying that as a commercial, but just so you know that the recommendations I'm giving you today come from a lot of experience, years of experience, walking press rooms and plants, probably that look a lot like yours. So here's the plan. We're going to talk about spray impact across the product line. We're going to follow the lubricant from the coil to the last forming station, stopping wherever it gets sprayed. We'll touch on 5 different aspects of lubrication spray for production. First, what uncontrolled lubrication actually costs, and I'll show you the math to prove it. Second, spray fundamentals. 5 variables. We'll go over all the variables and how they affect the spray, nozzle selection, and how drop size impacts your lubrication application. Third, we'll talk about lubrication applications along the line, stamping, sheet and metal, placement and zoning, roll forming, and fabrication. Next, we'll talk about automated control, closed loop spray, line speed tracking, recipes, maintenance, and troubleshooting. And finally, the business case, how to sell it to management, and how to do an audit checklist you can walk on your own line and do this week. Then we'll close with Q&A. So before anything else, let's go over the thesis of this whole session. In your plant, press speed is controlled to the decimal. Tonnage, also controlled. Material spec is controlled. Die condition, tracked and maintained. But lubricant application, which is really the only variable that's in direct physical contact with your tooling on every single stroke, that's usually set by eye and only adjusted if there's a complaint. Somebody often just opens a valve until it looks like there's a spray coming out, and then it stays set there until someone downstream complains about defects, galling, or about oil on the floor. If you leave today with one lesson, it's this one. Lubricant is a process variable, not a consumable line item. Treat it like this, and it will pay you back with less scrap and money saved. Okay, so let's start with how it really costs you if you're not controlling your lubricant. I'm going to show you 3 things. The 4 places lubricant touches your part, the 4 ways that can go wrong, and then we'll put a real dollar figure on it. And these are figures you can rebuild with your own numbers at your own plant. First, the fundamentals. What exactly is lubrication film actually doing? It's really doing 4 different jobs. It reduces friction between the material and the tooling. It protects your dies against galling, scoring, scratching, and wear, which leads directly to how long your tool lasts. It also makes parts more consistent because a stable film becomes part of the process instead of a variable inside of it. And also, it lets you hold quality at different speeds. Every shift, every operator, no matter if your line speed is changing. Now this part surprises some people. More lubricant is not always better. We're not just trying to apply the most oil possible. Extra lubricant does not do a job better than the precision, effective minimum amount. What you're going to do is you're going to want to apply the right amount, the right time, every shift. You don't want to overspray. You don't want oil all over your plant, on your equipment, and in places where you don't need it. The goal, minimum effective amount applied consistently. So where does lubricant actually touch the part? There's 4 possible places. You probably see it in all 4 in your plant. First, coil and strip. This is pre-lube applied to the strip, both sides, full width, before it ever reaches the press. Second, blanking. A metered film on the blank, which is where usually rollers, drip bars, and an operator's brush are used, instead of precise spray. Third, forming and drawing. This is the film that's on the blank and the die at the moment of the stroke, and this is the one that really governs your tool life. Finally, secondary operations. This is re-lubrication at roll forming, bending, and fabrication stations downstream. Now, the part you need to know is that each of these have their own spray applications with their own spray pattern, flow, and timing requirements. And errors in any one of these steps is going to compound and cause more scrap at the end of the day. So what happens when lubrication film is uncontrolled? Well, it fails in 4 recognizable ways that you see up here. So you might see a lot of these on your own floor today. One is over-application. Like we talked about, it's not about just dumping as much oil as possible. Over-application leads to cleanup labor, slip hazards, lost scrap value, and carryover that follows washers, welders, and paint lines in the area. Another way we see defects is uneven coverage. If there's dry spots, this can cause galling, scoring, and premature tool wear. And that usually gets blamed on the lubricant chemistry, the material itself, but the real problem is usually the spray distribution. 3, overspray and misting. This is atomized lubricant that never actually reaches the part. It goes into the air, into your people's breathing zone, and onto the floor 2 bays away. 4, speed drift. So if an application is tied to time instead of parts, you'll get a heavy film when the line runs slow and dry tooling when it runs fast. You need to be able to adjust how much you're applying based on the line speed. These are a lot of symptoms of one root cause. The spray is unmeasured, so the process is uncontrolled. Now let's talk about money. What is this actually costing you? There's 4 different buckets of costs that we might see. You might see some of these in your plant, and you might see all of these. First, consumption. You don't want to be using too much material if it's not needed. If you're using rollers, or you're using a drip or an open pipe, that's probably using 2 to 3 times the lubricant of a metered spray film that is controlled. The other thing that people often miss is you're actually paying for that twice. Every extra gallon you buy of material, you have to buy it and then you have to dispose of it. And disposing of it costs money as well. Then there's the tool. Die repair, unplanned downtime, and galling scrap. This is probably the largest number of money that you're losing, and also the least tracked one. Replacing or repairing a tool is not cheap. Finally, EHS. Airborne mist and floor oil drive housekeeping labor and recordable incidents, and this just causes a lot of extra downtime and safety issues. And these are kind of ranges that we've observed across multiple metal forming accounts. So let's do the math on one press. What you see up here are all estimates, but they're in the range of what we've seen in the field. Let's say the press is delivering 18 gallons of lubricant per shift. That's a real number from a real roller setup. But although you're using 18 gallons, the part really only needs 7 gallons applied to it. The cost of just purchasing those gallons of material, $22. That's not even counting the disposal costs I talked about, just the price of the material. Let's say you're running 480 shifts a year. 11 excess gallons times $22 times 480 shifts. It's about $116,000 a year. That's just on one press alone. That doesn't include disposal, cleanup labor, die repair, and the scrap parts. The audit checklist at the end can give you these inputs, and you can take these and calculate what's happening in your plant. And that is the money you could be saving by properly controlling your lubricant instead of just spraying without any sort of metering at all. Okay, so now we understand what the impact of spray is on the lubrication process. So how does that spray work? What variables can we use to control it? So this is the physics section. If you're an engineer, this is the part for you. We're going to uncover 5 variables that decide coverage. Then we're going to learn how to choose a spray pattern, how to pick a nozzle, and why drop size is so important. Every spray application is governed by 5 variables. Capacity. This is flow per time at a given pressure. This could be in gallons per minute, liters per minute, gallons per hour, whatever it might be. We usually use gallons per minute as our standard. This sets the film thickness before anything else does. Next, pattern. Your spray pattern could be a wide variety of shapes. Flat fan, full cone, hollow cone, solid stream. All these can be changed to match the geometry of the target. Spray distribution. This is how the volume spreads across the pattern width, because equal flow can still mean unequal film. It could be heavier on the edges. It could be heavier in the middle. These are all things that can be controlled. Atomization of the spray. This leads to drop size. Too fine of drop size and it's going to drift away as mist. It's not even going to reach the target. If the drop size is too coarse, it will beat up and puddle. Finally, spray impact. First of all, you want to make sure that you're spraying when the part is actually there. And then once you're spraying, you want to be able to calculate the force of the surface, and that's the impact on the part. Change any of these variables, and the film changes. The film of lubricant changes, and that's how you control it. All 5 of these can be characterized in a spray lab under your operating conditions before the system even reaches your line. Pattern selection and spray mechanism are concrete choices. And here's the cheat sheet for what you have to do to choose those. So there are a wide variety of spray patterns. For most of the lubrication applications, you're going to use either a flat fan or a full cone. Flat fan is used with strip and coil for full width lubrication. You want to overlap the sprays in the header to lay an even film against the width of the strip. Full cone, this is more used for die and cavity lubrication, where wetted area matters more than a defined edge. Once you pick your pattern, you also need to pick the spray mechanism. You can use an air atomized nozzle, or you can use a hydraulic electrically actuated nozzle that does not use air at all. So, air atomizing, it creates thin, uniform films of drawing lubricant. It creates very, very fine droplets, using compressed air to break up the spray. This is more what you want to use for viscous lubricants, so the fluid can probably be broken up into fine droplets. If you have a less viscous material, you're going to want to use electrically actuated nozzles. These are hydraulically actuated, so there's no air breaking up the pattern, and that way you get less mist in the air. And the electric part of it uses precise dosing timing. Basically, it's only going to spray where you need it, when you need it. That's the basis of zoned lubrication, which we'll spend some more time on later. There's also two other specs at the bottom here that a lot of people miss. Overlap is how you're going to overlap the adjacent patterns to give you a good intersection and an even spray. If you have gaps, you're going to get stripes and places where no lubricant is applied. Also important is the standoff distance. Pattern width is a function of distance. So if you move the header of nozzles just 3 inches, your whole spec just changed. Spray height from the target is very important. So now that you know all these variables, how do you actually pick a nozzle? You don't want to just go to a catalog and pick it. We have thousands of nozzles in our catalog, and that can get overwhelming. The selection should be driven from the application. Here's 7 questions you want to consider. What surface needs coverage? Is it a strip, a blank, a die? How wide is the target? Is it moving? How fast is it moving? Do you need continuous or do you need intermittent spray? What film thickness does the forming actually require? Are you running with a low or high viscosity lubricant? And finally, is misting a concern? Answer these questions and the nozzle choice basically makes itself. The best nozzle depends on lubricant type, film thickness, material width, and line speed. The answers to these questions pick the nozzle, not the other way around. Drop size. We touched on this a little bit already, but drop size is not just a detail. It's the difference between lubricant on your part and just lubricant wasted in the air. Too fine, and the drops never reach the surface. They just drift into the air as mist. It might look like great coverage when you're standing there, but actually it's airborne loss, dirty air, and oil on the floor. If your droplets are too coarse, the drops will beat and run. They'll be heavy in puddles and then dry in between. What you want is specified. Drop size measured under operating conditions. Your fluid, your pressure, and then hold it there by controlling pressure and air. So here's kind of the takeaway of what we just learned about with our spray fundamentals. Film control versus, I'm going to redo that, sorry. This is the takeaway of what we just learned about spray fundamentals. On the left side there, you see if you're using conventional methods like a roller, drip, you're manually applying or you're just flooding with open piping. On the right, you see precision spray controlled. So, film control. If we're using conventional methods, you set it once, and then variables might drift over time, your line speed, the temperature, and nothing is adjusted. With precision spray, you can meter per stroke, and it's independent of line speed. Placement. Conventional methods wet the whole surface, including areas that don't actually need any lubricant. Precision is zoned, applying lubricant only where you need it. Changeover. Manual resetup and operator-dependent repeatability is what you're going to see. Every shift might be different. But with precision spray controlled, you have a recipe that can be recalled, tied to the part number, and is identical every one, no matter what the shift is. There's a housekeeping aspect of it. If you have overspray all on the floor, all in your equipment, and you have mist where people are breathing it in, that's a big problem. With controlled spray, your overspray is basically eliminated, and you have less mist in the air, and less cleanup. Finally, verification methods. Manual, you might just say, looks wet enough to me. But if you monitor and control your spray, you can have an alarm go when the application goes out of spec, and you can make any adjustments needed. Okay, so now let's put this on your equipment. This is where the fundamentals turn into hardware on real lines: stamping, sheet and coil, placement and zoning, roll forming, and fabrication. In the middle of this, I'll show you a short video so you can see for yourself what controlled application actually looks like. Precision stamping lubrication. This is the flagship application for nozzles. Electrically actuated nozzles fire in sync with the press, applying the metered film to the strip, the blank, or the die, zone by zone, stroke by stroke. 4 things that changes. Application rate becomes independent of line speed. So no more heavy spray at slow line speed and dry spray at fast, where you're missing tons of spots. You can put different rates on different zones of the same blank. More where the draw is severe, less where it isn't. And then recipes are stored per part number and we're called a changeover. So this is kind of a direct upgrade path from a manual roller or brush application. It's more of a retrofit instead of a rebuild. The numbers on the right are from a real installation. 25% oil reduction observed, and production costs on that operation cut in half. So for the coil processors and blankers on the call, here's what you'll see. Sheet and coil lubrication, you'll have headers above and below the pass line that coat both surfaces full width, and nothing touches the sheet. So no marks on it, there's no roller wear or streaking to manage. Edge control matters more than people expect. Nozzles switch off across the width to match a narrower coil, so lubricant never runs off the strip edge onto the floor. If you have viscous fluids, heated delivery can help, drawing compounds and waxes that resist even application at room temperature. Here's a quick example. A manufacturer applying heated wax to strip before stamping raised production 20%. The interesting part is that the fluid change was enabled by the application method, and not the other way around. Okay, what about spray placement? Where do I place my nozzles, and how do I control which zone is spraying what? So where a nozzle points matters as much as what flows through it. First, aim at the draw. Target the severe draw zones, corners, and deep features. You don't want to be targeting the whole blank equally. Strip or die. Headers above and below the strip, or spray bars aimed at the die, chosen per operation and often both. You want to make sure also that your standoff is engineered. Mounting distance and overlap need to be calculated, not fixed. They do need to be fixed, not adjusted by hand until it looks right. If you keep adjusting your spray height or your overlap, all these other variables are going to change. Finally, zone by zone control. Each nozzle or bank is addressed separately, so one blank can carry 3 different film rates. Zoning is how you stop paying to lubricate steel that never gets drawn. And remember, placement is a drawing, not a habit. Standoff and overlap are the 2 most skipped specs on a header layout. Everything downstream of the press relubricates too, usually with the least controlled methods in the plant. So roll forming lines, here's what you want. You want metered spray at the entry, and between passes, you want to be replacing the flood recirculation. You don't want to just be flooding with everything. Less carry off, cleaner rolls, drier product at the exit. For tube and pipe mills, targeted lubrication at the forming and sizing stands, applied only while the strip is moving, so no puddles building up at every line stop. For fabrication cells, bending, punching, and trimming stations get a light, repeatable film instead of an operator's spray can. Same physics as the press. Pattern, replacement, and dose. Just size to the station instead of borrowed from it. Okay, so here's a good example of what precision spray lubrication might look like. I want you to watch how controlled this is, the edge where the film is stopped, how there's no mist in the air, and how it stops where there's no part underneath it. You see the spray is only on when it's needed. The overlap is perfect so that it's getting a even, thin coating. Nothing is on the floor, nothing is on the equipment. You can see the edge of the pattern is exactly where the part ends. You can also see these are pulsing on and off so that you can change your application rate depending on your line speed. You don't have to just vary pressure to do that. You can just change how often these are pulsing on and off. These are not using compressed air, so no misting in the air. This is a good example here of what you can do with the duty cycle, which is how often it's pulsing on and off. You see that as the line speed increases, we change our duty cycle to match it, and we're applying the same application rate despite the line speed changing. You can also use zone control, which can turn off individual nozzles if the geometry of the part is going to be updated. So you can see here, they switched to a thinner part, and they turned off whatever nozzles were not going to be spraying out of the part. That is full control. Let's talk more about overspray and mist and what this is really costing you. Lubricant in the air is lubricant you bought and never used. Then you have mist in the breathing zone, which drives ventilation costs and exposure monitoring. You also get oil all over, on the floors, guards, and conveyors, all your equipment, which is a slip risk and is housekeeping. Also, this might carry on to welding, joining, and finishing, all the other areas of the plant, and it's just going to mess up your whole process too. So here's how precision spray removes it. Drop size. If you specify drop size, it will be large enough to land, but small enough to spread. Then you want a triggered application so the spray is only there when the part is present, like we saw in that earlier video. You want edge control so that the spray is only on the strip and not on the floor. And you want lower pressure but the same coverage. You get less shear and less fogging in the air. Housekeeping is sometimes the improvement your operators will notice first as well. Usually within the first shift, people will notice that there's less oil all over the equipment, less oil in the air. It'll improve right away. Okay, so how do we fully control a nozzle? We know all the ways that we use nozzles, position them. We know the physics behind the nozzle. How do we turn a nozzle on and off? How do we control its flow rate? How do we do all that remotely? This is called precision spray control, and we'll go over the hardware that delivers it, recipes, maintenance, and troubleshooting. So nozzles apply the lubricant, but the controller is what makes the application repeatable. There are 4 elements to this. Sensing. We use sensors to see where the part is, or take a press signal or line speed, and input it into our system. Next, dose. So nozzles cycle at high frequency, and that way you can vary the volume without changing the pressure. Zone control. Each nozzle or bank is addressed separately and controlled separately, so the coverage matches the part, not the header. The part can change, the header stays there, and whatever nozzles you need are turned on and off as they're needed. And you can confirm all these things with monitors and sensors to monitor your flow so that out-of-spec application is caught before any scrap happens. Putting all this together, you get accurate, consistent lubrication on a wide range of fluids with minimal waste, and you can actually put a number on this. One of the biggest variables that's going to be changed in a production line is line speed. So how do we respond to this and keep application rate the same? So the controller reads press strokes or an encoder and scales the dose to production. Grams per part. Think of it that way. If you speed up, you slow down, or you stop for a die change, the film is going to stay the same. Same application rate every time. The dose is per stroke or per foot of strip. The spray then stops automatically with the line, so you get no puddles when it pauses. The first part after restart will carry the same film as the 1000th one. The application rate of your dye was proved out with the rate of seas on every shift at every speed. This whole thing is killing the heavy at slow speeds, dry at fast speeds cycle. That's it. Same application rate, any speed. So the core technology is precision spray control. Traditionally, a nozzle has its flow adjusted by changing pressure, but that also changes spray angle and drop size. Precision spray control electrically actuates the nozzles at a high frequency, pulsing them on and off like we said. This varies the flow without touching the pressure at all. So on the left there you see the old way, which was changing pressure in order to change flow rate. On the right you see precision spray control, the PSC way. So if you change pressure, your spray angle changes, your drop size changes, your pattern changes. If you use PSC, the flow does change, but everything else stays consistent. Consistent angle, consistent drop size, controlled flow, and uniform coverage. Okay, so here's the hardware that delivers that precision spray control. On the far left there, you see pulsar jet nozzles. Those are the electrically actuated ones I was talking about that pulse on and off to vary your flow rate without changing your pressure. In the middle there, you see our JXM nozzles. This is if you need air atomizing because maybe you have a viscous lubricant. They stay automatically aligned even after replacement, and they give you very consistent coverage and very fine droplets. So what controls these nozzles? It might look something like the AutoJet spray controller there in the middle. We have several different options depending on how much smarts you need to run your line, but all of them have repeatable timing and oil volume with a touchscreen to set all your settings. You're also going to want to use smart sensors for feedback. So you're going to want to track flow and pressure especially, and you want to receive automatic alerts as well when something goes wrong on the line.
Okay.
How does this all factor into quality control? Well, we use recipes so that every shift, every speed, every line speed, any sort of variable can be set with the recipe so that every time the same part is there, it'll be the same application rate. So it's basically one recipe per part. It can include volume, zones, and timing, and is stored with the part number. You select it at changeover, and you don't just do it every time from memory. That's why it's shift-proof. Third shift runs exactly what first shift ran because it's not up to the operator's judgment. It's just built into the recipe. This leads to faster setup as well. It's not a trial and error step in the sequence. Even if you're changing parts, you just input the recipe and you're ready to go. And all this is qualifiable. A documented set point is something you can control against and audit against. That way you make sure your quality is staying the same. The quality argument might be even simpler than the cost argument. An unmeasured input cannot appear in a control. Here's a hidden variable with fluid delivery: maintenance. So you might not realize it, but spray nozzles are precision components. They wear before the problem is visible. A nozzle doesn't just spray until it stops. The orifice wears out, and it's going to go out of spec. It might take a few months, it might take a few years, but the orifice will eventually erode so that you're dumping way more material than you should be. And you can't see it with the naked eye. Now, what you're going to want to do is you're going to want to test the flow rate to watch for nozzle wear. And you're also going to want to test for nozzle clogging as well. Also, you're going to want to check for misalignment and damaged spray tips. This is something you can at least see with the naked eye. If you can measure your pressure, you want to be looking for variation at the nozzle, which could be a sign of wear as well. Contaminated lubricant or filter maintenance that might have been skipped is not another thing to worry about that will not help with nozzle wear. Here's what you need to do on the right here. Proper filtration, clean tanks, correct pump sizing, correct pipe size, and valves. You want a stable pressure at the nozzle, and you want consistent lubricant viscosity. The nozzle orifice is often the smallest restriction in the entire system. So you need to be aware that means it's the first place usually that contamination lands. So when you have a lubrication problem, what are the causes? What could be the spray variable that might be causing these issues? I feel like this table will help a lot with troubleshooting. You want to be spending all day when a tool is down, when you could just maybe you need to change the nozzle. Maybe you need to look for these things that might be happening. So let's see you're seeing dry spots. This could be clogging in the nozzle. This could be your overlap isn't quite right and you have gaps. You could have too low of a flow. Maybe you're not applying enough pressure, or maybe your nozzles are misaligned. What if I'm seeing too much lubricant? That could mean your pressure or your flow is too high. Your line speed might have slowed down without you noticing, or your timing might be a little off in your controls. Or maybe, like we said, your nozzles are worn and they're just dumping more than they should because they have an opened up orifice. Misting is another big problem you're going to see. That could be from excessive pressure. You could have the wrong drop size. Like we said, if your drop size is too small, it's just going to atomize into the air before it even reaches the part. Or maybe you're not spraying on your target. You're just spraying onto the equipment and misting everything in the air. And finally, if you see part defects, if you're scrapping a lot of parts, it could be from uneven film. You might not be applying enough film, or there might be contamination in your material. These are all things you want to check before trying to rebuild the tool or do anything more drastic. A lot of these can be caused by spray issues. You want proof before and after install. So here's what you want to do to make sure you're measuring everything. You want your drop size measured and spray performance characterized in a laboratory under simulated operating conditions, which is something we do for customers all the time. Then during the design, we can do CFD modeling, which sizes the nozzles and it will confirm the overlap and the positioning before anything is even made. And then after everything is installed, we want to be able to monitor your flow with alarms, and we'll be there with local support so that if you're having some sort of variation among shifts, you're having any sort of problem, we can help you troubleshoot. Every claim I've made in this session can be tested on your line before you buy the system, and that's the proof you need. Okay, so now how do we make the business case? How can you really measure improvement from using a precision spray instead of just a manual roller or an open pipe? We're at the end of this, we're going to show a 6-question audit that you can run this week in your plant, which will give you a roadmap for implementation. And then at the end of this, we'll do some Q&A. So here's the first rule of the business case. You want a baseline before you change anything. You want to document where you are today, and then you want to track the results after the changes. Here are some things you're going to want to track. Lubricant use per shift per part. Tooling maintenance frequency. Lubrication-related downtime. Part quality consistency. Scrap and rework weight. Cleaning time per week. Safety incidents and slip hazards. And operator adjustments per shift. If you can measure all these things, you have a baseline. Document where you are now, make one change, switch to a nozzle, switch to a controlled nozzle, then measure again. Here's a business case that management will accept. Line 1, fluid purchase avoided. Metered volume uses less fluid, and whatever price you're using for it, that's money saved. Line 2, disposable and treatment. Like we said, you buy the material, but you also have to dispose of it. You have to take it out of your facility and properly dispose of it, which is also costly. Housekeeping labor. The hours per week your people spend cleaning floors, guards, and conveyors. Tool life and scrapped. So die repair intervals, gallening rejects, unplanned downtime, these all lead to scrap parts, and they all lead to worse tool life. Throughput. You're going to have faster changeovers, less downtime, fewer stoppages. In most projects that I've scoped, you might honestly get the payback just from line 1, just from the material. But just thinking about line 2 through 5, that makes it obvious. So here's what I want you to do. Walk your own line this week and ask these questions. 1. Do you know how many gallons per shift each press actively applies? 2. Is a set point written down per part number or set by the operator? How is that controlled? 3. Does the application rate change when the line speeds up or slows down? 4. How much lubricant ends up on the floor, the conveyor, or in the air? How many gallons of lubricant are you using, and how many do you need? 5. When were the nozzles last inspected for wear or plugging? 6. If the application failed mid-shift, would you find out on the line? Or would you find out on the customer? Would you find out with scrap parts? Here's the standard. Any question you cannot answer with the number is a project with scoping. And when you do this audit and you find a potential project, a potential improvement, here's how you run it. First, define the lubrication goal. What does good look like? In numbers. Document your current issues and costs, and that will be your baseline. Then audit spray coverage and delivery, the whole system. Select the right nozzle, strategy, what nozzle do you need to use, and also where you need to place it, what overlap do you need to use. Put it on a drawing, write it down. Then add controls where the process needs repeatability. Then train operators in maintenance. The system holds spec, but the people are going to keep it in spec. Then track results and adjust as needed. Notice the hardware doesn't even show up until step 4. You're not even implementing anything until then. First, the audit finds the project, then the roadmap, the one you see here, runs it, one press at a time. So 3 concrete offers before we go to questions. You could do a spray audit. A local engineer walks your line, measures current application, and reports what's recoverable. Or a lab evaluation. You can send us your lubricant, your part geometry, send us all your information. We can characterize the spray performance before anything is even implemented or installed. Also, a resource pack. Metal forming lubrication notes, case studies, troubleshooting table, everything for this presentation. My contact information is right here, and feel free to email me with any questions or for any of these resources. So what are the takeaways I want you to have here? Well, lubrication affects quality, tooling, safety, and cost. More lubricant does not mean better lubrication. Uniform targeted application is the goal. Minimum effective amount applied consistently. Line speed, nozzle condition, placement, all these things matter as much as the fluid you buy. Automation improves repeatability across multiple shifts, across multiple operators. And then maintenance is what keeps your performance consistent. Small changes produce measurable gains. That's it. That's what I want you to take from this. Now, bring me your problems, bring me your concerns. I want to open up to Q&A. What are you seeing at your plant? What concerns do you have, and how do you see the possibility of precision spray helping your process? So, open floor now. Use the Q&A panel, and I'll read each question aloud and then answer them. Bring anything specific from your plant, dry spots, overspray, uneven coverage, whatever you're seeing. And one last reminder, that spray audit is real. That will be the next step if you're interested. Thank you all for spending time with the PMA and with me.
Terrific. Thank you, Sam. Really excellent presentation. Certainly apologize for the technical issues, but we made it through. So we'll go ahead and open up the floor to questions. What's going on in your plants related to lubrication challenges? I've got a few questions as well. We can get started, but we want to hear from everybody online with us. If you've got some lubrication issues you'd like to discuss with Sam, go ahead and fire away. The first question I've got, Sam, is if companies are already using roller coaters and it seems like they're working just fine, how might they know, or what would be the clues that they actually might have a lubrication problem?
Yeah, I would say with roller coating, there's a few things you can look for. You can look for extra lubricant being applied, the film not being very thin at all. It's just kind of being applied on heavily. also extra lubricant on the floor and on the equipment around it because you really have no control over where that's going. And then look at your scrap rate. How many parts are you scrapping because there might be voids or defects? That's probably because you're not applying the lubricant very evenly because of the roller that you're using.
Okay, good. Um, so when you visit shops or talk to customers, what's the single most common mistake you can isolate one that you see when it comes to how stampers are applying their lubricant?
Yeah, and this is something I touched on a lot in the presentation, but more lubricant it isn't always good. Often people think I just need to apply as much oil as possible, and that's the proper way, to apply lubricant. But in reality, you want to use as little as possible in the most efficient way. That way, you're not wasting a bunch of material and you're not applying oil where it's not needed.
Gotcha. Okay. Okay, a couple from the audience here. If a customer wants to use a new fluid, I always ask this question too. What's the process for testing that fluid? Obviously without interrupting production. But how do you recommend companies evaluate new fluids using your equipment?
Yeah, for us, the most important thing is viscosity. So if you give us the viscosity of a new fluid, we can test that here in house. We can basically match any viscosity you have and do a test in our lab and see what the spray performance is and then report it to you. And then ideally, if you have any downtime and also can install the nozzle with the new fluid and really test your application, that's the best way to know as well.
Very good. Okay, another one from the audience. One of our first steps for building the case is defining your lubrication goals, right? So how do you determine how much lubricant a part actually needs for forming? Is there a good way to measure how much lubricant is actually making it onto the part? That's a pretty good question.
Yeah, there are a few different ways to do that. You can measure transfer efficiency, which is a percentage of the fluid that leaves the nozzle and that is actually applied to the part. Usually you do that by weight. That's the easiest way.
Okay.
And then as far as how much lubricant the part needs, I mean, that's kind of dependent on how little lubricant you can apply and avoid any scrap parts, right? So if we're applying as thin a film as we can, and we know we're hitting the areas that need to be hit on the part, then we know you're going to get a successful part. But that's very application specific, and that's something we can work with you on site.
Okay. What about stamping simulation programs? Is there any success out there in using simulation to help with lubricant or not? Not really.
We definitely can do some simulation here. We usually do just simulations of the nozzles themselves. That would be
Okay.
CFD. We have a whole CFD team here that can do simulations.
Okay.
And often the customer will build that into if they have a simulation for the whole system as well, they can build that in.
Excellent. Yeah, I stopped it. So your email is not on the screen. What's your email address?
It's just my name at spray.com. So sam.scully@spray.com.
Is it further back in the slides?
Probably.
Or I don't see it. So you're it's not gonna read it. Okay.
I think we'll also, if I'm not mistaken, send out an email blast with my contact info after this as well.
Okay. Well, yeah, we can do that. There's another good question. Do you have any method for where the lubricant targets the pierce or shave punches that are not exposed in a coil blanking operation?
So I think are we talking about basically spraying into hidden areas here, I would assume?
I think that's what he's talking about. Yeah.
Yeah, I mean, I'd have to see the system and everything, and this could be a good thing to follow up with offline, but often we use robotic arms or to get into hard to reach places. And we'll mount our spray guns to those arms and they can kind of get into the crevices and hidden geometries that you need to spray. So that could be good for that.
Yeah. Okay. Randy, I see your question, but I'm not really sure if you want to rephrase that, I'm not really sure. Randy says our sprays into a roller, so no real way to reduce when vacuum roller is turned on, all the lubricant is off of blank. I'm not sure what he's getting at.
Yeah, I'm not sure exactly what the setup looks like that he's referencing, but we can certainly work with them. That might just be a simple switch from a roller to just a line of nozzles, and you would get a lot better quality.
Okay. We're a minute over, but I'm going to ask one more question that I've got, and then we'll see if anybody else has any more questions. Since we had a little delay there with the technology, we'll keep it open if people still have questions. So the question is, we've got a press that runs at variable speed, and you talked about this during the presentation, but how do you keep the film thickness consistent when the line speeds up and slows down? Somehow you're sensing the line speed through the press control or something like.
Yes. Yeah, that was kind of, if you saw the videos that we showed, and we'll share those with you after as well, but you can vary the duty cycle of the nozzle. So as the line speed increases, you can spray more frequently to make sure your application rate is staying the same. The other thing you can do, and this is all from inputs of the line speed into our controllers. Once you have that line speed, you can do that duty cycle variation, and you can also vary how long the nozzle is on for. So if the line speed increases, you're going to turn the nozzle on and off more quickly to make sure you're not overspraying when the part is gone. So you're just spraying when the part is underneath you. Both of those things can be tied to the line speed input.
Very good. Very good. All right. Any other questions from our audience? We've still got plenty of people online. All right. Then thank you, Sam, for a really excellent presentation. Really nice use of graphics and videos to hammer home your points. To the audience today, thank you so much for attending the program. And apologies for the technical issues, but thanks for hanging in there with us. We do hope you found it to be valuable. Once again, an archive of today's webinar will be available on our website within the next day or two. So when that's ready, you'll receive an email from us with a link so that you can access it online and review what you learned today, and perhaps share it with others in your organization that might benefit from the information that Sam presented here today. So again, thank you, Sam. Thank you, Spraying Systems, and thank you to our attendees today. Have a great afternoon. You go ahead and close your browsers now.